Okay, we've introduced carboxylic acids, gone through part one, kind of how you name them and that sort of thing. And now we're going to focus on reactions of carboxylic acids. We're going to focus on esters, what they are, and how do you make esters, and then the reactions of esters. So that's where we're kind of headed here. This is pretty much review right here. It's showing you how you would prepare a carboxylic acid. Two ways. You could start with a primary alcohol and oxidize it all the way to a carboxylic acid, or you could start with an aldehyde. It'd already be halfway there, and oxidize it to a carboxylic acid. So that's review. You're already familiar with those. As a matter of fact, you should have a couple of those on the homework. Did have a couple of them on the homework. Just hand it in. And that's our favorite oxidation slide. Okay, the first thing carboxylic acids do is when you put them in water, they dissociate. This is the first organic molecule you're finding to behave this way. Alcohols don't do this. When we say an alcohol dissolves in water, we're just saying that it is soluble in water, but it does not dissociate. But a carboxylic acid will. So if we had some acetic acid like this, and we put it in water, we would get the acetate anion and the hydronium ion, and this hydrogen here on the water, the hydronium ion, is what makes the solution now acidic. Makes it acidic. This is why carboxylic acids are acids. If you do this with methanol or ethanol, the alcohol that's in alcoholic beverages, you put this into water, you just get ethanol in water. It dissolves in there, but the hydrogen stays on the molecule. The molecule does not dissociate. And so the pH here is going to be approximately 7, maybe 6 to 8, neutral. But the pH here with vinegar is going to be about a pH of about 3.5. It's going to be acidic. All right, so we're making much of these being acids, but let me just clarify. These are not, if you take HCl, if you make an acid with hydrochloric acid, that is a very strong acid. All of a sudden I feel like I'm left out of something here. This is a new way of taking notes. What?
It's for the Google Docs.
It's for the Google Docs. Oh, okay. Okay. So everybody's putting in their email address? Okay, great.
So you don't have to do it.
So I don't have to do it. I'm happy. All right. All right. So hydrochloric acid is a strong acid. You should have heard these terms in 1305. It's a strong acid. It dissociates completely, and it would make water pH of about 1. Very low pH, or less than 1. But vinegar or acetic acid makes it about 3.5. It's a weak acid. Yeah, these are weak. Carboxylic acids are weak acids. All right? These are some of the things you should remember. I mean, I could say carboxylic acids are strong acid, strong base, weak base, neutral. All right? So you should be able to pick it out. It is a weak base. Excuse me, weak acid. Weak acid. Weak acids. All right, this is why you can swallow this, but you can't swallow hydrochloric acid without tearing away the epithelial layer of your esophagus. It will corrode your tissue, but vinegar doesn't. It'll pickle. If anybody made pickles and you worked with vinegar solutions and your fingers get all kind of wrinkled up because it's pickling your skin a little bit, but it doesn't react with it. Okay, second, we'll move along pretty quickly here. We're going to go through this list of reactions today. So that was just dissociation. You put it in water, it dissociates. They are acids. So you can react a carboxylic acid with a base and you form a salt and water. Now again, I keep alluding back to 1305. If you took hydrochloric acid plus sodium hydroxide, it would form sodium chloride and water. So an acid plus a base forms a salt and water. This is neutralization. The acid is acidic, the base is basic. They react with one another and they neutralize one another. They bring them back not to being acidic or basic, but neutral. Particularly if you react equal molar amounts of them together, then you end up with just salt water. Your end product is just salt water. In this case, the salt is sodium chloride, but over here, the salt can be something else. So let's again work with our favorite molecule, or at least my favorite molecule. Acetic acid, and let's name it here. Acetic acid, because I want you to see what happens to the name. It is also called ethanoic acid. And we're going to react it with sodium hydroxide. And the OH, this hydrogen here is going to combine with that OH to form water. This sodium is going to combine with the acid here to form this salt. That's going to be a negatively charged anion and the sodium plus ion and water. That's a balanced equation here. Where'd that H2O come from? H2O. Okay, we know what H2O is. It's water. But let's name this other thing here. So to name this, we're going to put the metal name in the front, sodium. And then what I'm going to do here, I'm going to drop this IC and add ATE to the name. So the acetic acid is going to become acetate. And the salt there is called sodium acetate. That's the common name. And the IUPAC name, we would do the exact same thing. Just drop that IC. So drop the IC and add ATE. So this is going to be sodium ethanoate. Sodium ethanoate. That's the name of that salt. It's got two names, common and IUPAC. I'm kind of dwelling on this. We're going to dwell on naming because when we get into esters, you're going to see this ATE ending coming up from now on, whether we're naming a salt or an ester. And where are we deriving it from? We're deriving it from the original name of the acid. What was the acid called? We're going to drop the ic, add ate. And this is a neutralization reaction. A carboxylic acid plus a base is going to form this. This is this slide here. I don't know. We're going to drop the ic, not the OIC. We just drop the IC and add ATE. First, add the cation's name, sodium, and then you get acetate. If it was benzoic acid, you'd have sodium benzoate. Here are a few examples of some uses of carboxylic acids, or the sodium salts, or the salts of those. Soap, we'll talk about this here. This is the reaction by which you make soap. But this is a soap molecule. It's a sodium salt of, this would have been stearic acid, so you have sodium stearate. And that is a very common, if you made soap out of beef fat, in the old-fashioned way. Old-fashioned means 150 years ago, when people were trying to make soap, and they would take beef, they would take the fat of beef and get the fats out of it and react it with lye, they'd make soap. And they would make that kind of soap, sodium stearate. They're used as preservatives. Calcium propanoate or sodium propanoate are preservatives. Here is an antifungal where zinc is the ion, not sodium, but zinc and this undeclinate, that's 2, 8, that's 10, 11. So undeclinate. So declinate would be 10 carbons long, but undeclinate is 11 carbons long. With the zinc, and you got athlete's foot medication. Zinc 10 undeclinate. And then you can take something like citric acid or other carboxylic acids, make the sodium salt of them, and the mixture of those two becomes a buffer. And what is a buffer? A buffer is a mixture of a weak acid and the salt of the weak acid, which stabilizes pH. If it gets subjected to an acid, it absorbs it and neutralizes that by the equilibrium that's set up there, and keeps the pH pretty steady. So if you have a food that on the shelf you want it to be pH 3.5 and you want it to stay right there, you can put a buffer system in there and it'll stay at 3.5, rather than if there's some process going on that's going to make it more and more acidic and make it go bad. You got a buffer. Okay, why don't you take just a minute or two, and try to finish these reactions. Here's 3 quick reactions. Just try to write those, and then we'll get into some of these a little more complicated reactions. What esters are. This chromate here is an oxidizing agent. Okay, the top one can oxidize in 2 steps, can't it? We got a primary alcohol, and it can oxidize to what? What first? An aldehyde. So there's the aldehyde, and that aldehyde can oxidize to the carboxylic acid. The second reaction, the middle one there, we're starting with an aldehyde. All right, so there's only one product that we would anticipate there. We got pentanal, an aldehyde, going to, just like right above it, but a different carboxylic acid. This would be pentanoic acid. I think I write a little better when I'm sitting down. Okay, so pentanal becomes pentanoic acid. So those are oxidation reactions. This third one is the acid-base reaction. We're starting out with propanoic acid, and we're reacting it with this base here, potassium hydroxide. And we're still going to end up with 3 carbons here, and our oxygen. We're going to lose the hydrogen, and it's going to be replaced with the potassium ion, and the hydrogen is going to combine with the OH of the KOH and form water. Does anybody want to take a stab at naming that product for the last reaction? What do we call that? Okay, that's a very good start. Potassium. Potassium what? Propanoate. 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 So we're going to just drop the IC and add the ATE. So propanoic becomes propanoate. Propanoate. Okay. Good, good. It's always kind of good to stop for just a second and solidify this. Let's go on. Just for your information, you don't have to write this reaction, but this is kind of interesting. This has a environmental science value to it. McDonald's, do you think we produce a lot of potato peels? Do you think McDonald's produces a lot of potato peels? Yeah. Okay, they're peeling all these potatoes. Either potato peels and or if you're, yeah, there's other ways of peeling potatoes, or at least getting the skins off of them besides peeling them. But what you can do with organic waste like that, food waste, is you can feed it to bacteria. They can chew on it and produce lactic acid. That lactic acid can be harvested off of this foodstuffs, any kind of organic matter, corn husks, anything. You can bacteria will break it on down into lactic acid. You can polymerize it and make PLA, polylactic acid, And you make plastic out of it, plastic film. You can make plastic bags out of polylactic acid. And what's the beauty of that? They will decay. You put them in a landfill and the bacteria will chew them up. They don't stick around for 3,000 years like our Ziploc baggies do. 3 or 4 years ago, I forget how long ago it was, Lay's potato chips on Earth Day wanted to release, and as a matter of fact they did, release their little sun chip bags in polylactic acid bags. And you know, and they were saying this is a kind of our Earth Day special. You can throw the bags in the landfill and they'll decompose. And I don't know if they've kept up with that or not. I do know they ran into problems because their suppliers of polylactic acid couldn't get enough lactic acid to make all of this stuff. So the delivery system for that approach didn't work. But pay attention to plastic bags and see if you, sometimes they will say what the bag is made out of or whether it's biodegradable. And if it's biodegradable, see if it is saying it's polylactic acid. I haven't paid real close attention, but I lost track of that story. But that's what Lay's potato chips tried to do about 5 years ago. Now maybe they got it back up again. I think California has some pretty strict environmental laws, and I think they really were trying to promote this, and there might have been enough to do this in like California, but not nationally. Okay, this chapter is really kind of broken up into two key parts, carboxylic acids and esters. So now we need to understand what esters are. They're similar. Here's your carboxylic acid, and here is your ester. Okay, if you drop that hydrogen and add a carbon of some sort, not just one carbon, it could be 1, it could be 10, it could be 3, whatever, you can form an ester. So the ester linkage is a carbon-oxygen double bond and a carbon-oxygen-carbon bond, which is an ether. So you have the ether and the carbonyl makes up an ester. That's the ester functional group. These are neat molecules. If I blindfolded you and walked you into HEB and I said, okay, we're going to wander through the fruit and vegetable section and I want you to try to tell me where you are, you would be able to smell the bananas. You might, if there were plenty of strawberries, if there were plenty of strawberries, you'd say, oh, I think I'm near the strawberries. Oh, I smell pineapple. When you're smelling those things, you are detecting an ester. That's what they're giving off, esters. Volatile little molecules that have a pleasant aroma. That's generally the case with esters. They're mildly polar. They're not as polar as the carboxylic acids because the carboxylic acid has this bond, which is very polar. But the esters have these bonds, not as polar. They are more polar than an alkane. They're more polar than just carbon-carbon bonds. You do have oxygens here, and they tend to attract electrons towards them. So make a little kind of a negative character here, but they're not anywhere near as polar as an OH bond. That's about all you need to know. So there's slight water solubility, but you build up the carbon chain on either either end of the ester, and it's not going to be very soluble in water. All right, here are some examples. Here's what, if you smell pineapple, this is what you're smelling, ethyl butanoate. And we'll do a deeper dive into this, but just to pay a little bit of attention, Here's an ethyl. There's your ethyl group. Butanoate. All right? And you can imagine that came from butanoic acid. If you put a hydrogen right here, you'd have butanoic acid. So what do we have? We have ethyl butanoate. Common name, ethyl butyrate. And there's each one of these fruits has its own. So isobutyl formate. So it would have been formic acid. It's now in an ester, isobutyl formate. Here's the acetate we drew earlier. So what do we have here? 2-methyl butyl acetate, or isoamyl acetate. It's an isoamyl group. Isoamyl, no, where'd it go? Isoamyl acetate. Is that the one I just did? Yeah. Here's oranges. 8 carbons long, octyl, and 2 carbons long, acetate. You're seeing the common and the IUPAC names here. Apples. Methyl butanoate. Fragrance from apples. And apricots, pentyl. 1, 2, 3, 4, 5. So we have got a pentyl butanoate, or pentyl butyrate. Okay, the first, and this is a key reaction. How do you make an ester? This is the answer to that question. By esterification. And it is a dehydration reaction. The removal of water from between 2 molecules. Esterification, you form an ester linkage. Okay, here is a good general description of it. General description of esterification. A carboxylic acid plus an alcohol forms an ester plus water. It says dehydration. So you are forming, water is one of the products. You're removing water from between those 2 molecules. Now I'm going to write these down here carefully. We're going to look at this. Up there we got propanoic acid and methanol or methyl alcohol, and we're getting an ester. Plus water. So let's do a deeper dive. So the general reaction is a carboxylic acid plus an alcohol forms an ester and water. Okay, now let me just get the start of our product right here. Got 3 carbons. Okay, I'm going to stop there for a minute. I just want you to get this settled in your head right here. This portion of the ester is coming from here. You can see that. We've got everything we have over here except that hydrogen. Right? This means right. So there's what we got. And then we're going to split this water out of here. Here's where the water is coming from, right here. This is the dehydration. We're pulling this water out from between 2 molecules. chemists would say these molecules are condensing on one another. Two separate molecules are now becoming one compound, being condensed or consolidated into one molecule. So the only thing left over here is that methyl. Okay? So when you look at these reactions, be real clear about what part, where does this part come from? An alcohol. Where does this part come from? A carboxylic acid. You're going to always know what part came from the carboxylic acid because it's going to carry this. All right? The alcohol is not going to carry that. There's not going to be any carbon-oxygen double bond coming from the alcohol portion. There wasn't any there in the first place. So this is from your carboxylic acid. This is from your alcohol. Okay, now let's look at the name. This is propanoic acid, and this is ethyl, and I'm going to use its common name, ethyl alcohol. And so in the ester, we're going to begin with the portion of the name that came from the alcohol. So this, I'm sorry, it's not ethyl alcohol, it's methyl. Sorry, methyl alcohol. I was just testing you, seeing if someone would correct me. All right, so this is methyl. That's the first portion of the name, methyl. And the second portion of the name is going to be what? Propanoate. Propanoate. Because all we do is just drop that ick and add ate. And this is our ester. That's why it's called esterification. It's a reaction by which you can form an ester. And it's a very versatile reaction. You change, you could have 20 different carboxylic acids, 2 or 3 different alcohols. You can make a ton of different esters. All right? So different alcohol, different carboxylic acid, you get a different ester. Esterification. This is a reaction that those of you in 1107 will do, making aspirin. And this is aspirin right here. Acetyl salicylic acid. You start with salicylic acid. It is carboxylic acid, but it has an alcohol functional group right here. So if you react that with acetic anhydride, you form an ester. This is going on here to form this right here, and you have a carbon-oxygen double bond, carbon-oxygen carbon bond. So there's your ester linkage in aspirin. Don't worry about writing all of that. I don't expect you to memorize salicylic acid. Polyesters. And notice up here it has phenyl is COOH, ethylene glycol. Let's just look at that a little bit more carefully down here. Here's your phenyl group. And this looks like benzoic acid. Well, it is. That's benzoic acid right there. But the terphthalic acid has an OH on either end. Para. So para to this is another carboxyl group. And then ethylene glycol has an OH on either end. So it's alcohol functional on both ends. This is carboxylic acid functional on both ends. So you can split water out here. And just imagine you can have another terephthalate over here. And you can split water out over here. And you could have another ethylene glycol over here. And another here, and another here. And then pretty soon we're over in the CCC building drawing this polymer. All right? And I've just fallen 3 floors. Don't want to do that. But you can see what that is. You're building a polymer, a nice linear polymer. That's a polyester. Polyester. Because you're going to get an ester here. You're going to get another ester here, ester here. It's going to be this polymer that's held together by repeating ester linkages. And you can make fabric out of it. So you see a garment, it's 35% polyester and 65% cotton. Mylar, plastic bottles. If you turn over your water bottle, let's see what mine. Put the cap on first. Well, I don't see it on the bottom of my bottle. Mine's all crinkled up. So. Well, looking for PETE or the 1. See here? PETE. That's polyethylene terephthalate. So look for either that or a kind of a little triangle that kind of looks like this. There's a number 1 in it, real tiny, stamped into the plastic. That is the symbol. So that triangle with a 1 in it is referring to it being polyethylene terephthalate. That has it?
Oh yeah, I see it. And it says PET.
There you go, polyethylene terephthalate. So that's a polyester bottle. All right, you melt that down. If you were to melt that down and pull it into fibers, pull it into really fine little fibers, you could make a garment out of it. And then you'd have polyester thread.
Should we make a 3x5 card for that side?
For the polyester, no. No, these things are more or less for the PLA, the polylactic acid, the PETE, just for your awareness. These are esters that you've come across. Okay, so no, I don't expect you to reproduce that reaction for me. Okay, nomenclature, a little bit more on nomenclature of esters. All right, they are produced from a carboxylic acid and alcohol. The name is derived from that origin. All right, so if we look at this molecule, we see we have a methyl here, and we have a 2-carbon carboxylate. Now I know that this came from the carboxylic acid because I can see the carbonyl right here, the carbon-oxygen double bond. So, and there's 2 carbons here. So that is ethanoic acid or ethanoate, methyl ethanoate. Well, let me use that one as example here for a second. I want to show you, I'm going to repeat that one right here. So that's what we have right here. But what if we had a 1-carbon carboxylic acid and a 2-carbon alcohol? Came from a 2-carbon alcohol. I mean, total, I got 3 carbons. 1, 2, 3. 1, 2, 3. But the number of carbons that would have come from the alcohol is different. The number of carbons that would have been on the original carboxylic acid are different. These two molecules are going to end up with very different names. Not very different, but different names. So we just named that one, methyl ethanoate. Ethanoate. What are we going to call this one? Ethyl methanoate. All right. I want to use two molecules that pretty similar, but you can't just jump in here and say, oh, that's methyl ethanoate. No, it isn't. It's ethyl methanoate. You've got to say how many carboxylic acid did that come from? A 1 carbon. You follow me? That would have come from this acid. And that's methanoic acid. Now, Leah, this is one you should have a 3x5 card for. What is its other name? What is the other common name for methanoic acid? Test time, you know the answer to this. And it is? Okay, there's a slide in here. Yeah, what is it? Formic acid. Formic acid. So, what is the other name here? It's going to be ethyl what? Convert the formic acid into the ester name. Formic becomes, well, it becomes close train. Here we don't need the O because there's no O there to begin with. Formic is just IC. So all we have to do is take off the IC and add ATE. Formate. Okay, so get pretty familiar with acetic becoming acetate and formic becoming formate. Otherwise it'll throw you. I'll say, I could say, I will say it right now. I'm going to say it. Do this, draw isopropyl formate. Okay, that could be a question. I say draw a structure. Okay, draw isopropyl formate. Isopropyl formate. So formate is that. How many carbons are in isopropyl? 3. And where is it attached to the formate?
First? No, that's the other.
Where?
Yes.
It is attached to the oxygen right here, right? On which carbon? We've got 3 carbon.
The middle one?
The middle one. Because see, isopropyl alcohol looks like this. Isopropyl alcohol looks like that, and if that is going to be the alcohol that's going to react with formic acid, we're going to split the water out right here. So it is going to be that middle carbon. It's where that OH was that is going to bind to the ester. Follow me? So we're going to get that carbon there, and this carbon here, and that carbon there. And we've got isopropyl formate. If it was propyl formate, it would be attached to the end. But this is isopropyl formate. Yeah, this is good. You should be able to go from a name to a structure, or from a structure to a name for esters. Naming esters, here's just a few more examples. So there's ethyl. You can see that came from the alcohol, that came from the carboxylic acid. Ethyl came from butanoic acid, so get ethyl butanoate. The apple fragrance was what? I think methyl butanoate? One of the fragrances might have been this. One of the fruit fragrances, ethyl butanoate. Okay, see, here's where the propyl is attached on the end, and we're just calling it propyl, distinguishing it from isopropyl. So we got propyl ethanoate. This just kind of shows you that whether we're naming a salt, sodium ethanoate, or naming an ester, ethyl ethanoate, we're using the same name for the carboxyl portion of the compound, whether it's the salt or the ester form. So if you don't have a hydrogen there, you should be adding ATE to the name. Not the ick, but converting it over to the ATE form, whether you're talking about a salt or an ester. Okay, I think on the homework I referred to this as acid hydrolysis. Acid hydrolysis. And you can see right here, here's our acid. Now we're moving on into the heading. We kind of know what an ester is. We've dealt a little bit with how to name esters. And now what we're dealing with is, okay, how do esters react? There are two reactions. I got them in reverse order here. We'll look at acid hydrolysis. I kind of like to look at this because this is the reverse of this. Notice it's just esterification backwards. You take an ester, you react it with water in the presence of an acid, and what do you get? A carboxylic acid and an alcohol. You're breaking the ester back down into the things that it was made from in the beginning. Okay, do you see that? We're going to insert the water molecule back in here. We're going to put a hydrogen on this oxygen and an OH on this R group, this portion of it, and we get our carboxylic acid and alcohol back again. So here is an example. Here is propanoate plus water in the presence of an acid, and it will break up, it'll convert this to the carboxylic acid, propanoic acid. It'll convert the propyl to 1-propanol. There's no water over there. We had to use water here as a reactant. This is the hydration or hydrolysis of this molecule to form our carboxylic acid and alcohol. Okay, I'm not going to dwell on that. I want to take at least 5 minutes. So come back and look at this. The saponification reaction is a little bit more complicated. So saponification. And I need to correct this slide. This is reacting with sodium hydroxide. All right, sodium hydroxide is actually a reactant here. And you're going to get the salt of the carboxylic acid and an alcohol. Now, here is the most common, this is a pretty complicated molecule. It's a triglyceride. We'll study this in chapter 17. Triglyceride. It is a triester. There are 3 esters linking these fatty acids to the glycerol backbone. And so you can take that and react it with 3 sodium hydroxides and break it apart and form soap. Okay, this goes into a little deeper dive here. So let's, down here it says M could be sodium or potassium. I'm going to change it to sodium because that's the most common form here. We're going to get a sodium, and a sodium. So we're getting 3 molecules here. You can see there's a plus sign means you got 1, 2, 3. Each one of these is going to form that salt. We're going to get the sodium right here. And put a hydroxide on there to form this alcohol. This triol, glycerol. And that is the soap molecule here. It has this dual character of a long chain, which is nonpolar, and a polar, and matter of fact, charged end. This end here is very water-loving, hydrophilic, and the tail on this molecule is hydrophobic. And so these soap molecules are surfactants, they're surface active agents. What surface? They're operating at the surface between water and oil. Where those two kind of things combine or meet, that's where soap finds itself. The long chain is down into the oil, and the carboxyl group is in the water. It's right there, and you mix that around, and you can form an emulsion. You can emulsify the oil and the water. That's how soap works. Because on one molecule you have a water-loving and a oil-loving portion of the molecule. And it can emulsify oils into water. So that's why we use soap. We have oils on our hands, or we are working with meats and have fat on our hands. You take the soap and it'll emulsify it and wash it off. Yeah, this is kind of showing it. You can see that in the water you have the soap filling a film on the water. One portion of the molecule likes the water and the other portion doesn't. You mix it and you can emulsify oil in water in these little micelles, or these little droplets of oil surrounded by or dissolved in them are the tails, the soap molecules, and the edge of the soap molecules are pushing out towards the water. Okay, there's a few slides to pick up on. in terms of phosphate esters, but I don't think those are on the homework. So I would say the homework should be due on Monday. Okay, you got till Monday to do the homework. I'll be ready for chapter 15 on Monday. We'll polish up a few slides left over on chapter 14 and go into chapter 15.